In this organic chemistry screencast, we're going to look at one-dimensional and two-dimensional NMR spectroscopy to elucidate the structure when we're given a molecular formula of C6H12O and infrared data with 1718 in reciprocal centimeters. The first thing we're going to want to do is calculate the degrees of unsaturation that are present in the molecular formula, and what that's going to tell us if there's a pi bond or a ring present. At this point, we don't know exactly what. We'll just determine if there is a degree of unsaturation present. So we have C6H12O, and again, we're going to use the general formula for an alkane, H2N plus 2. We have N is equal to 6. We plug it in there, and we're going to end up with C6H14. So we have to modify what we are given to get rid of the heteroatom, and basically oxygen neither adds nor subtracts to the hydrogen count, so we have C6H12. And we're going to take that and subtract it away from what it should be to get H2, and we know that a molecule of H2 is equal to a degree of unsaturation, so we actually get 1 degree of unsaturation. The infrared data has a peak at 1718 reciprocal centimeters, and what that is telling us is that that is a carbon-oxygen double bond, so a carbonyl group with 2 bonding substituents. And what is that? That is 1 degree of unsaturation, and we just calculated from up here the molecule has a degree of unsaturation. So we know that a fragment in the molecule thus far is a carbonyl group. And so what is a carbonyl group? It is CO. So what we can do now is take our given molecular formula, C6H12O, that had 1 degree of unsaturation. We're going to subtract out what we know, and that's the carbonyl group, to end up with C5H12 that has no degrees of unsaturation. So what does that tell us? That these carbons are all sp3 hybridized. That means they're fully saturated. They can't be part of a pi bond. They cannot be in the alkene region or the aromatic region of the NMR spectra that we're going to look at. So let's go ahead and look at the proton NMR. This is taken at 600 megahertz. So what is that telling us? Just briefly. So if we look at, say, between 1.4 and 2.4, that is 1 part per million, and that is equal to 600 hertz. So that's a little bit about the scale that we're working with. So what I've done already is measured the height of the integral, and those numbers are in red. All I did was take a ruler and measured from here, extend this line. Then with a simple ruler I made measurements, and these are in millimeters. So that gets the height, and so that's equivalent to the area under the curve here, and what we're looking for is a ratio of what these peak heights or areas are to one another. So let's go ahead and make a table. I'm going to, for now, just label these from left to right. I'll call this A, B, C, D, and E. So we can make our table here A, B, C, D, and E. So we measured 13, 20, 13, 13, and 20. So these are measurements in millimeters, and we want to find the ratios to each other. So we're going to divide all of those by the smallest number, which is 13. which gets us 1, 1.5, 1, 1, and 1.5. We can't have 0.5 of a proton, so we multiply by 2, which is an integer. So we basically need to get whole number integers here. So in our next column, we multiply by 2 to get 2, 3, 2, 2, and 3. So what I'm going to do under the integrals here is write those numbers. So that's 2, 3, 2, 2, and 3. Now if we add all that up, we have 2 plus 3 is 5, plus 2 is 7, plus 2 is 9, plus 3 is 12 hydrogens. So that matches what we were given originally in the molecular formula, so we've accounted for all the hydrogens. And those hydrogens are distributed amongst 1, 2, 3, 4, 5. So we have 5 unique type of hydrogen. So at this point, let's go look at the carbon-13 NMR. And notice this is run at 150 megahertz. It's the same instrument. It detects both proton and carbon nuclei using the same probe. But basically, 1 part per million on this scale is worth 150 hertz. The first thing we want to do, we're going to ignore the solvent. We're not counting those, and we're going to count the unique number of peaks that we see. So I'm going to label these from left to right as 1, 2, 3, 4, 5, and 6. So we have 6 unique type of carbon. And again, from the molecular formula, we have 6 carbons. So we've accounted for all of the carbons. All of them are unique. One thing I want to point out is notice that we have 6 unique type of carbon, 5 unique type of H. So we can infer from that one of those carbons does not have any hydrogens. And we already know that from the IR data. And it is this sp2 hybridized carbon that does not bear any hydrogens. And we can actually make that assignment right now, that the carbon at approximately 210 parts per million belongs to that carbonyl. Because remember up here, we said that all the other 5 carbons have to be sp3 hybridized, and so we have this distinction between them. We have carbon 1, which is much downfield from the rest of this cluster, which is 5 carbons here. So if we count 2, 3, 4, 5, 6, that cluster is 5 carbons worth. So we know that those 5 are all sp3 hybridized. Those 5 have the 12 hydrogens. So now let's sort of use both the proton and the carbon data together to make some assignments. So if we're looking at the proton data, say A, B, C, D, and E, we're going to look at the integrations that we found. That carbon A was worth 2 hydrogens, so we can say that is a CH2 group. Carbon B is worth 3, that's a CH3 group. C is 2, that's CH2. D was 2, CH2. And E was 3, so that's CH3. So we've accounted now for all of the carbons, the 6 unique carbons, all of the hydrogens, and the oxygen as part of a carbonyl. Now what we can do is start putting these fragments together based on using the coupling constants of the proton NMR. And so let's read them again from left to right. We'll determine the number of neighbors based on how the peak multiplicity looks. Let's go ahead and make another table so this is clear. We'll do it right here. So A, B, C, D, and E. A, we see 3 peaks, so that's a triplet. B, we see 1 peak, that's a singlet. C, we count 1, 2, 3, 4, 5 peaks. We'll call that a quintet or a pentet. D, we count 1, 2, 3, 4, 5, 6 peaks. We'll call that a sextet. E, we count 1, 2, 3. That's a triplet. So based on those multiplicities, we can use the n+1 rule to figure out how many neighbors are bonded to that. So peak A is a triplet, which means that it has 2 neighbors, so 2 + 1 gives you the triplet. So in this next column here, we'll just write 2. B is a singlet. That means there's no neighbors, so 0 + 1 is a singlet. We're going to put 0 neighbors. Quintet is 5, so that has 4 neighbors. Sextet is 6, so that has 5 neighbors. And again, a triplet has 2 neighbors. So that's going to help us piece these fragments together. So if we look at how we can start this, putting these fragments together, let's consider the clustering of peaks in the proton NMR, where we have this gap between, say, 1.6 and 2.1. So we have this clustering of peaks here, and then this clustering of peaks more upfield. The peaks between 2.1 and 2.6 are in the allylic region. And what does that mean? That they are directly next door to some sort of pi bond. We already know the molecule has a pi bond in terms of a carbonyl. We know that peak B has 0 neighbors, so we know that's going to be directly bonded to the carbonyl. And so in terms of a proposed structure, we have a CH3 group with no neighbors bonded to a carbonyl. We then move over, so we can say this is B. We have a CH2 group in the same chemical and shift environment, so that's going to be carbon A. Carbon A, the protons appear as a triplet, so we know that that has to have 2 neighbors. And then we're looking at the rest of these that we have to assign. We need C, D, and E. So C has 4 neighbors, D has 5 neighbors, and E has 3 neighbors. So if we just continue out the chain and just draw CH2, CH2, CH3, we can basically put in now C, D, and E. We said that C has 4 neighbors, and we can see that from the adjacent methylene groups. D has 5. That's the CH3 of E and the CH2 of C. So this would be, at this point, a structural claim. And so what we're ending up with is a ketone, the name of which it has 6 carbons, so it's a hexane derivative. The carbonyl is at position 2, so we're going to call it 2-hexanone. So even though we have a structural claim at this point, let's go ahead and look at this 2D NMR data so that we can understand how this helps us basically give confidence to the structural assignment we've already made. So let's first look at the HHQC spectrum here. I'm going to write in those arbitrary assignments that we've made already. And that's just A, B, C, D, and E, reading from left to right. So down the diagonal is a thick red line, which basically means the two projections on that line are identity. So E is E, D is D, C is C, B is B, A is A. What I'm going to do now in the blue marker here is draw a cross peak that crosses that line. So if we're reading here, let's read sort of this way. And so when we hit peak A and we read down, we're running into this peak. And what I want to do is basically, once I hit that, I want to go back to the other projection. So that I'm going back this way. And I can say that A is coupled to C. Another way you can do this is basically look at all the peaks and draw a cross line that bisects the diagonal, and from there you can make these same relationships. So you have AC, or alternatively CA. We do that same thing here. We have CD or DC. This would be D coupled to E, E coupled to D. So basically on either side of that diagonal is basically the mirrored coupling that you have to observe. So what do we do with this information? Let's go ahead and tabulate it here beneath our proposed structure. So we're saying A is coupled to C, C is coupled to D, and D is coupled to E. So we can basically substitute those things into one another and end up with the following relationship. A to C to D to E. And if you look at our structure above, we actually see that. We see A to C to D to E. So that's the line that we just figured out from the 1H cozy. So we basically, what we're doing is figuring out this spin system. A to C to D to E. So we already have a structural claim of 2-hexanone. Let's go ahead and look at the proton-carbon HSQC spectrum. Go ahead and put in those assignments A, B, C, D, E. Number the carbons. Notice this carbon's at 45. It was carbon 2 from our carbon spectrum. 3, 4, 5, and 6. We're just counting those carbons here. The black peak indicates the phase. So black peaks are CH3 peaks. The lighter peaks are CH2 peaks. And what this spectrum is telling us is the actual assignment of the proton bonded to that direct carbon. So if we're reading this way, we hit peak A, we come down, we see that it's bonded to a CH2 group, and that's carbon 2. So we know from our prior cozy assignments, let's go ahead and draw in those. We had B, A, C, D, E. So what the HSQC is telling us, we know that where the proton assignments of A are, we can come over and get the carbon assignment. So that carbon is 2, has a chemical shift of about 44 parts per million. We come over now to B, we go down, we're hitting a CH3 group, so we know that B has to be a CH3 group. We come over to here and we make that assignment as carbon 3. Notice that these numbers are not the absolute IUPAC numbering of the name. We're just doing it for simplicity's sake to map the proton assignments, the carbon assignments, and then the correlated assignments. All right, continuing on to C, we see that that's a CH2 group. We're coming over back to the carbon projection, and we're running into 4. So we can call carbon 4 is there. The same thing for D, we're coming down, we hit a CH2 group. That's carbon 5. E, we come down, we hit a CH3 group. We come back over to the carbon projection, and we're going to make that assignment as 6. So notice that the HSQC data is direct H to C correlation. Notice that the sp2 hybridized carbon, which does not have hydrogens, does not show up on this projection. And so it's, again, a direct H to C correlation. So if the carbon does not have hydrogens, you're not going to see a peak in this piece of data. Moving on to the last bit of 2D NMR spectra, that's HMBC. So now these are not direct HC. These are going out 2 or 3 bond couplings away. So it's basically mapping out further than what the HSQC is telling us. Let's go ahead and redraw this structure again. Put those assignments back in. So the HMBC does show. So I'm going to go ahead and label the carbon projections here now in blue. 1, 2, 3, 4, 5, 6. Let's go ahead and put our prior carbon numbering in. We said this was 3. This was 2, this was 4, this was 5, this was 6. The sp2 hybridized carbon now shows up. Again, that's carbon 1. Our proton assignments from before were B, A, C, D, and E. So what I want to do is make a table here. We're going to read the spectrum. Again, we're going to read the proton projection from left to right, so we're going to start reading this way. We hit peak assignment A first, then we read down. We see that this is going to be A5, So A sees 5, and what that is specifically, this hydrogen, HA, sees this carbon. So if we count the number of bonds there, that's 1, 2, 3. So I'm going to write columns here, 2 and 3 bonds. So A sees 5 through a 3-bond connection. You can see that in the column of A, there are multiple peaks. So A sees 4 as well. So for HA to see C4, that's a 2-bond correlation. It also sees 3. That's going to be a 3-bond correlation. And going further down, it sees 1. So A1, that is a 2-bond. So what we're doing is basically mapping out all these different relationships. Let's go ahead and now we're moving on to the B protons. We're coming down this column. We can see that a B sees carbon 2. That's going to be a 3-bond. Further down, B sees carbon 1. That's going to be a 2-bond. Those are the correlations we have for B. We now move on to C. So we have C seeing 6. That's going to be 3-bond. We have C seeing 5. That's going to be 2-bond. C sees 2. That's 2-bond. C also sees 1. That's 3-bond. So we've written down 4 relationships for C. Moving on to D, you can see that D has 3 relationships. So we have D6, that's 2-bond. D4, that's 2-bond. D2, that's a 3-bond. That's all the relationships for D. So we move to E. We see E has 2. So E5, that's a 2-bond. So E5 was a 2-bond correlation. Now we have E4. That's a 3-bond correlation. And so what this is helping us is to map out these different relationships amongst the proton and carbon through multiple bond correlations. So what you're doing is you're counting the bond from the indicated hydrogen atom through to the adjacent carbons. And so you end up with these relationships that help us map our proposed structure and prove that it can only be that and not something else. So this has been a screencast on the assignment of a structure from the molecular formula using degrees of unsaturation, infrared data to tell us functional groups, proton and carbon NMR to tell us the unique sets and integrations, and then the two-dimensional data to tell us the correlations between the different proton-proton, proton-carbon assignments.